Hello, I'm Alexey, and I'll be talking about this problem. We have a standard data type, and if we load this type in GHC, derive show, we get a nice representation of all the name, email, and everything. And the question is, how does GHC know to make this nice instance? Because obviously there's some work going on here. You could obviously write it by hand, but how does it do it automatically? How do we do the same for our types and our type classes? Probably different ones. So let's have an example. We have this simple serializing-like type class where every data type that implements 2 bits can go and serialize itself to a sequence of zeros and ones. And let's write a few simple instances. Here is the simplest data type we could come up with, unit. And if we want to serialize it, there is nothing we can serialize, so we just leave it like that, and empty list. Here is the sum data type, might be either, but I've defined it like that just to illustrate the point. And we can serialize it pretty easily. If we get in the left one value, we can put a 0 in front. If we get another value, we can get a 1 in front, and that's nice. So here's an instance. And for a product, we can serialize both by serializing the first one and serializing the second one. Now, the thing is, if we roll these 3 instances, we can mechanically write instances for pretty much any algebraic data type. Let's have some examples. An empty tuple corresponds to unit. Maybe corresponds to a sum of unit and the data type that we started with. A list corresponds to a sum of unit and a product of that element and the rest of the list. If you've been to Sean's talk this morning, then you've seen all these algebraic derivations. And finally, the user type that we defined earlier, it's isomorphic to a product of text and another text. So that was name and email. So what we can do, what would be really nice to do, is write all instances in terms of unit, sum, and product, and then somehow convert our concrete data types that we have to a hierarchy of these data types. So this is a generic type class which you can use. Let's have an associated type for our original type. And we can convert between our data type and the associated data type. The conversion is total either way. There's no maybe, there's no undefined, there's nothing like. So we can do all of these things. And if we could get the compiler to generate this for us, and if we wrote all the instances for these types, sum, unit, and product, we could write that 2 bits instance for everything. But we can't write a show because you can see user had the email and name, and this just had a text and text. So if we just get a text and text and a product of them, we can't really do anything to show it. So let's expand the definition a bit. See, there are 2 data types which are isomorphic, but they differ in their record types. So what if we could define some additional data types that wrap the name of the records, the name of the constructor, and the name of the type themselves? Fortunately, we can use data types, type level strings in GHC to define the data types. If you can see, the values, the set of values is the same for A and this data NA, the constructor NA and selector NA. If it provides the functions that get this type level string back into our string, we'll be really all set. So let's have a few examples again. Empty tuple is a data type named empty tuple with a single constructor named empty tuple and the actual value set is unit. Maybe A is a data type named maybe, and it's actually a sum type with the first possibility is a constructor named nothing, the actual value is unit, and the construction of just, and the actual value is A. And so on for the sum, for the list, and for the user, where you can see finally we got name and email. So if we now operate on this extended type hierarchy, we can write our show, we can write equality, we can write OR, we can write anything that we really want. So this is a simplified description. Let's now go and see what GHC gives us. There's this module which has some, not ideally, in my opinion at least, named types, isomorphic to what we've seen just before. The unit, the sum, with a nice plus, type level plus, the product, and this leave data type with, let's just say it's rec0, and this is the representation. We can ignore all of this machinery, which was there to support some obsolete uses, but unfortunately have stayed in the library. And again, let's ignore P, which is a phantom parameter, which will be useful later. I can show it up later. So what happens is, and we've missed the type, constructor, and selector names. So again, don't worry too much about this representation as a new type. What's really interesting is how the isomorphism works. So a user is a data type with some meta information which I omitted that has a single constructor with some meta information of two selectors, a product of two selectors. These are both selectors with some meta information which I omitted, and both of them are texts. Same goes for the empty tuple, maybe integer, which is a concrete integer here. I omitted them because they're not just the names. They have in GHC pretty much all of the options that you can give to the data types, constructors, and selectors, such as laziness, unpackedness, and whatever other options GHC supports or might support in the future. So they look rather unwieldy. What you really get out of them is the data type name, constructor name, and selector name that you can get out of any value of this type. So it's going to be the same for all the types, for any type that we have here. The data type name is going to be the same for each value of this type. So you don't need an actual value. It's just based on the type. So let's see how it works in practice with our user type. We had a user with name and email, and we've derived generic. This is the magic that lets us derive all this isomorphism, which is still called rep, and which will later allow us to write our own instances. Kind, with an exclamation mark, gives a representation of the type that we give it. And so this associated type for the user is a data type with this metadata. These are the module name, if I'm not mistaken, and this might be the source file name. So there is a lot of metadata going on here. So for example, no source unpackedness and so on. So this data type has a single constructor with two selectors, a product of two selectors. The first selector is name and so on, and the actual value is a text. The second selector is email, and the actual value is text. So let's use this isomorphism. We can convert from this value of type user to the associated representation. And we get this this data type representation where the meta is not in the value, it's just the type level. So all this metadata is just on the type level, and the actual value, you can see that there are only two pieces of value, name and email. All the rest is the metadata that was there from the data type, constructor, and selector. And this is the actual value. Again, selector and the actual value. If we get a sum type like maybe, this is a just one with type maybe. So here we get the right value because there was two, nothing, and maybe. So of the two alternatives, we chose the right one, meta, 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 actual value. So let's use this to write an actual instance. For a better example in serialization, we'll try to convert any data type into form data of this style, where you can get a map of text to maybe text. So something like this: C and C equals 4 and B equals 3 and so far. JSON will be too boring, so there are instances for JSON in the JSON libraries that are widespread there. But what we want to do is we want to provide an instance from any value of our type to form data. So we're too lazy to write an instance for every single thing that we have. So let's use the generics. Let's modify this type class to form data to accept the default implementation that if our type A has a generic instance and its associated representation, that isomorphic thing, is an instance of this helper type class, then we can convert it. And how we convert it is we convert it to the representation first and then use this associated function, helper function. This is a pretty standard way of using the generic machinery to make our type classes support it. So what do we need to write in, like all the instances that we now need to write will be instances of this helper type class to form data prime. And what we have to do is, okay, let's start with a single value. We can't start with a single value because we don't know about the selector name. So we need to write an instance for the selector part. If we can go back to here, we can't write an instance just for this part, the text. This is actually the value. We have to get the selector value, which unfortunately is named M here and S here. It's really a lot of type aliases which looked very nice in the paper, but you have to deal with it now. So we get this value M, which is of this data type, and the A is the actual text inside. So we will do our thing and we'll pack the selector name and the value of text here. I'm simplifying this a bit. I'll only pack the text values. If you wanted to pack something else, you could show it, I suppose, or apply toForm data on them recursively. No, that doesn't work too well. You have to apply it and then escape it or something. So let's simplify things and keep it to the text. We can write the instances for product and sum pretty easily. Just let's convert both things here, and let's convert whatever is there that we have into form data. So this is a sum, this is a product. And finally, we have to deal with the outer layers of the meta, the data type, and the constructor names. So we just ignore them. If there is meta of data type, we'll ignore it. Constructors, we'll just ignore it. Obviously, if the concrete data types that we have needs to use some information in the data type or constructor names, you're welcome to use it. Right now, we only need the selector names. So we redefine our type user, which derives generic and toForm data. Because we've derived generic, that can automatically be derived by GHC, and it is of the exact shape that we've described here of meta, data types, constructors, sums, and products for every data type that's guaranteed. It satisfies toForm data prime. The only constraint is we can only have the text values. If it doesn't, then it doesn't satisfy the form data. So because we satisfy toForm data prime, we can now derive toForm data. The only member was toForm data, and that had a default instance, so we don't need to write even that. Or if it's not your data type for some reason, you can just say instance full-form data user, that's equivalent, and there is no methods. That's all you need to do. Let's do something else and reverse this. That bit that doesn't fit there, that's maybe A. So again, let's move it back from form data to back to our data type. Again, we define a supplementary type class which works on representations of those isomorphic representations, and we first apply that to get a representation, and we convert it back to the type that we want. For this one, let's be a bit lazy and say, unless we know otherwise, this bit here, overlappable, we don't care about any meta. And just go through it via fmap. Fmap here is needed because we produce a maybe value. For product, let's get the first bit, let's get the second bit, and tie them using that product. For sum, let's try parsing the first one, or let's try parsing the second one. And if, like, on the first one, let's put the left selector, on the right one, let's put the right selector, and that's how we construct the representation. And finally, the base case, which is we need to parse a single value which has a selector. We could apply cell name to any value of the right type, but we don't have it yet. Once we build it, we'll have it and we could apply cell name, but we need cell name to build anything. So what we do is we apply cell name to undefined of the right type. This M here is a critical bit, the meta information, which has a selector name. And because for all values of this type, the selector name is going to be the same thanks to the same M. It's just going to work. And once that's done, we look for that key. We see if it's a single value of that type, and we wrap it properly, and we get the instance of the right type back. I could have passed exactly the same type here as I had here, and this needs scope type variables extension. But they both work, since here I don't care about the actual record type, I just care about the meta information. That's fine. So what we can build? We can build show, we can build ORD, we can build equivalence. All of these are pretty trivial, even though for ORD and equivalence, we go on to two structures in parallel. And so if we want to compare two representations, we compare the first part. For a product, we compare both parts. For sums, we compare the corresponding things. We can't build an fmap because for fmap, the type of this value changes. So we can represent f from A, and we can represent f from B. What we can't represent f by itself. So there's another type class which you can derive again, where you can convert any, like if you have a data type of star to star kind, you can derives a generic 1. And again, this is all completely done by GHC. So if you just derive generic 1, you'll get back an instance of this. And you get some new building blocks of your parameter, that A here, and a recursive occurrence of yourself. So for example, for a list, it's a cons of parameter and the recursive occurrence. And also, let's see how this works. Let's define a pretty primitive lambda expression. That's an S expression, sorry. And we can derive generic and generic 1. So rep 1, that's the higher kind representation, is, again, a lot of metadata. And what we see in the end is, where did it go? Parameter occurrence corresponds to the constant here. Text, which is static, it doesn't change, so that's the same as in the user case. And finally, the recursive calls here, which are represented by these ones. So this is how we can build any kind of data types. There are a few limitations here. Generic gives you anything that you can do with a kind of star. Generic 1 gives you anything you can do with a kind of star to star. As far as I know, there is no higher kinds of generic, so there is no generic 2. And so if you implement something like dmap or bmap, like bfunctor or profunctor, out of luck. These things can be unwieldy. The error messages are surprisingly not gigantic, and you can understand, especially thanks to this indentation, what's going on and what is it trying to find an instance for. It'll typically, you forgot to write an instance for something like, let me go back to the user. Something like selectors or constructors. So you say you forgot about constructors. So it'll go through the data type and complain that it can't find an instance for your constructor. Fine, you just add one, which you'll probably skip through if you don't care, and you go through it. There are other libraries that are, OK. This is all main content. There are other libraries that are equivalent in GHC and other libraries. There's Scrap Your Boilerplate, which relies on higher order functions. It is similar but in intent, but it has a lot of intricacies if you want to write an equivalence. So if you want to show something, you're fine. If you want to compare two things in parallel, it's very sophisticated. The similar thing exists in PureScript. Unfortunately, due to type limitations of PureScript type system, they had to introduce a maybe in the from and to conversion, and so it doesn't work like that as well. And there's Uniplate, which builds onto generic for things that you might want to do with your generic types. For example, if you have a large data type, such as representation from pandoc of your Markdown document, you can find every link in there and replace it with a shortened version through your favorite URL shortener. That's all I have. There's a link to the talk. There's a link to the source code in the talk, which is still here. Questions?